Somewhere above the blur of atmosphere, in the thin black silence 300 miles overhead, a telescope the size of a school bus has been circling Earth for more than 30 years, its mirror quietly gathering light that left distant galaxies long before our sun was born. This is the story of Hubble, of the engineers and dreamers who built it, the flaw that nearly ended it, and the astronauts who reached up to give it new eyes. It is a story told slowly, with room to breathe, with no need to hold on to every word. If these quiet journeys help the mind settle toward rest, the subscribe button is always there, a small way to return whenever sleep feels far away. The year is 1946, and an astronomer named Lyman Spitzer has just written a paper that most of his colleagues will dismiss as fantasy. And so the story begins. In the autumn of 1923, a patient astronomer sat at the eyepiece of an enormous telescope on a mountain in California. And in the quietness of that long night, he began to understand something that would change forever the way human beings thought about their place in the darkness between the stars. His name was Edwin Powell Hubble, and he had come to Mount Wilson Observatory with the careful training of a lawyer, the steady hands of a former athlete, and the quiet persistence that belongs to those who are willing to look at the same patch of sky night after night, waiting for the universe to reveal its secrets in its own unhurried time. The telescope he used was the Hooker telescopes, which in those days possessed the largest mirror ever ground for astronomical purposes, a great disk of glass 100 inches across that gathered the faint light of distant objects and brought them into focus for whoever had the patience to sit in the cold mountain air and look. Hubble had been photographing a hazy patch of light in the constellation Andromeda, a smudge that astronomers had long called a spiral nebula, believing it to be a cloud of gas and forming stars somewhere within our own Milky Way galaxy. The prevailing wisdom of the time held that the Milky Way was essentially the entire universe, a vast island of stars, perhaps 300,000 light-years across, surrounded on all sides by empty and eternal darkness. But as Hubble examined his photographic plates that autumn, comparing images taken on different nights, he noticed something peculiar and wonderful. There were points of light within the Andromeda Nebula that changed in brightness over time, growing dimmer and then brighter again in a regular and predictable rhythm. He recognized these as Cepheid variable stars, a special class of pulsating stars whose true brightness could be calculated from the period of their variation. This relationship had been discovered years earlier by Henrietta Swan Leavitt, and it provided astronomers with a kind of cosmic measuring stick, a way to determine how far away these blinking beacons actually were. When Hubble performed his calculations, using the apparent brightness of the Cepheids he had found and comparing it to their true brightness as determined by their pulsation period, the numbers that emerged were almost impossible to believe. The Andromeda Nebula, that faint smudge of light, was not a cloud within our galaxy at all. It was a separate galaxy entirely, a vast congregation of billions of stars lying some 900,000 light-years away, far beyond the boundaries of the Milky Way itself. Later measurements would revise this distance to approximately 2.5 million light-years. But even the initial figure was sufficient to overturn centuries of assumption about the scale and nature of the cosmos. In one stroke of observation and careful reasoning, Edwin Hubble had expanded the known universe by an almost incomprehensible factor. The Milky Way was not alone. It was merely one galaxy among what would eventually prove to be hundreds of billions of galaxies, each containing hundreds of billions of stars, scattered across distances so vast that light itself required billions of years to traverse them. Our cosmic address had changed, and humanity found itself living not at the center of everything, but on a small rocky planet orbiting an ordinary star in the outer suburbs of one galaxy among countless others. It seems fitting, then, that when the time came to build a telescope capable of seeing deeper into space than any instrument before it, a telescope that would orbit high above the blurring atmosphere of Earth and gaze with perfect clarity at the most distant reaches of the universe, the scientists and engineers who dreamed of such a thing would choose to name it after Edwin Hubble, the man who had first shown us just how much there was to see. The idea of placing a telescope in space, above the layer of air that causes stars to twinkle and blurs the sharpest images into softness, had occurred to various thinkers over the years. But it was a young astrophysicist named Lyman Spitzer who first set down the argument in careful and persuasive detail. In 1946, only a year after the end of the Second World War, Spitzer wrote a paper with the rather dry title of Astronomical Advantages of an Extraterrestrial Observatory, and in its pages he laid out the case for building a large telescope that would operate not on any mountain, however high, but in the vacuum of space itself. Spitzer understood that the atmosphere of Earth, for all its life-giving properties, was a terrible impediment to astronomical observation. The air shimmers and shifts, bending light in unpredictable ways, and even on the clearest nights at the highest altitudes. This turbulence limits the sharpness of any image that can be obtained. A telescope in orbit would suffer no such limitation. It would see with a clarity impossible from the ground, resolving details 10 times finer than even the best earthbound instruments could manage. Furthermore, a space telescope could observe in wavelengths of light that the atmosphere absorbs completely, such as ultraviolet and certain bands of infrared, opening entire new windows onto the universe. Spitzer's paper was visionary, but in 1946, humanity had not yet placed so much as a simple satellite into orbit, and the notion of launching a precision optical instrument into space seemed almost fantastical. The paper was filed away, but the idea persisted, and as the decades passed and rocketry advanced, what had once seemed impossible began to seem merely very difficult. Through the 1960s and 70s, as astronauts walked on the moon and robotic probes explored the planets, the dream of a large space telescope gradually took more concrete form. Studies were commissioned, designs were proposed, and in 1977, the United States Congress approved funding for what was then called the Large Space Telescope, later to be renamed in honor of Edwin Hubble. The project would require the combined efforts of thousands of engineers, scientists, and technicians, and it would take more than a decade to bring to completion. At the heart of the telescope would be its primary mirror, a great disk of glass 2.4 meters in diameter, lightweight and precisely figured to focus starlight with extraordinary accuracy. The task of creating this mirror fell to the Perkin-Elmer Corporation, a company based in Danbury, Connecticut, with deep experience in precision optics. In their facilities, skilled opticians began the long and painstaking process of grinding and polishing the mirror blank into the exact shape required. A gentle curve that deviated from mathematical perfection by no more than a few millionths of an inch. The work proceeded slowly, as such delicate operations must, and the years accumulated as the mirror took form. Grinding and polishing optical glass to such exacting tolerances is an art as much as a science, requiring patience and care and the kind of attention to detail that cannot be rushed. The opticians at PerkinElmer used a device called a null corrector to test the shape of the mirror as they worked, bouncing light off its surface and analyzing the reflections to ensure that every portion of the curve matched the design specifications. Meanwhile, other components of the telescope were being designed and assembled across the country. The spacecraft that would house the mirror was being built by Lockheed at its facilities in Sunnyvale, California, a cylindrical structure 43 feet long and 14 feet in diameter, wrapped in silvery insulation and bristling with solar panels, antennas, and the delicate aperture door that would open to admit the light of distant stars. The scientific instruments that would record and analyze that light were being developed at various universities and research centers, each one a marvel of miniaturization and precision. The total cost of the project, when all was said and done, would exceed $1.5 billion, a staggering sum that reflected the unprecedented complexity of what was being attempted. No telescope of this size and sophistication had ever been launched into orbit. The engineering challenges were immense, from the need to keep the mirror at a stable temperature despite the extreme swings between orbital day and night, to the requirement that the entire spacecraft be able to point with extraordinary precision and hold that pointing for hours at a time while long exposures accumulated photons from the faintest and most distant objects in the universe. 15 years passed from the initial congressional approval to the day of launch. 15 years of design and fabrication and testing. 15 years during which the telescope was assembled and disassembled and tested again in vacuum chambers and vibration facilities, preparing it for the rigors of spaceflight. There were delays and setbacks along the way, as there always are with projects of such ambition, including a pause of several years following the Challenger disaster of 1986. When the entire Space Shuttle program was grounded for review and redesign. Finally, in the spring of 1990, the telescope was ready. It was loaded into the cargo bay of the Space Shuttle Discovery at the Kennedy Space Center in Florida, secured carefully within the orbiter's cavernous hold, awaiting the moment when it would be lifted beyond the atmosphere and released into the silent clarity of space. On April 24, 1990, Discovery rose from the launch pad on a pillar of flame and thunder, carrying the Hubble Space Telescope toward its permanent home in low Earth orbit. The crew of 5 included Commander Lauren Shriver, a veteran astronaut with the quiet competence that came from years of military test flying, and pilot Charles Bolden, who would go on many years later to serve as administrator of NASA, leading the agency through a new era of exploration. With them were mission specialists Stephen Hawley, Bruce McCandless, and Catherine Sullivan, each playing a role in the careful choreography of deployment. The shuttle climbed through the atmosphere, shedding its solid rocket boosters and external tank as it accelerated toward orbital velocity. And within minutes, it was circling Earth at an altitude of approximately 340 miles, higher than most shuttle missions flew, chosen specifically to place the telescope above the densest layers of atmosphere and reduce the drag that would slowly cause its orbit to decay over time. The deployment itself was a delicate operation, carried out with the shuttle's robotic arm, lifting the telescope from the cargo bay and holding it suspended in the blackness of space while its solar arrays unfurled and its systems came online. On April 25th, the arm released its grip, and the Hubble Space Telescope drifted free, beginning its solitary orbit around the planet, a cathedral of glass and gold sailing through the silence, its great mirror awaiting the first light of distant stars. From the ground, engineers at the Goddard Space Flight Center in Maryland began the process of activating and calibrating the telescope's systems, a methodical sequence that would take weeks to complete. Commands were uplinked, and data began to flow downward, telemetry indicating that the spacecraft was healthy and its systems were functioning. Anticipation built among the thousands of people who had contributed to the project, who had spent years or even decades of their careers working towards this moment when humanity would finally possess an eye in space capable of seeing the universe with unprecedented clarity. And then the first images arrived. They came down through the deep space network, converted from radio signals to digital data, reassembled into pictures on computer screens at Goddard. And as the scientists and engineers gathered to examine what the telescope had seen, a quiet realization began to spread through the room, a dawning understanding that something was not as it should be. The images were not sharp. The stars, which should have appeared as crisp points of light, were instead surrounded by fuzzy halos, their light smeared across the detector in a pattern that spoke of optical imperfection. The focus could not be achieved, no matter how the secondary mirror was adjusted. Careful analysis would soon reveal the cause: a flaw in the primary mirror itself, a deviation from the correct shape so subtle that it measured only 2 microns at its worst, roughly 1/50th the width of a human hair, yet sufficient to render the telescope incapable of achieving the sharp focus that was the entire purpose of its existence. Somewhere in the long and careful process of grinding and polishing at Perkin-Elmer, something had gone wrong. The null corrector used to test the mirror had been assembled with a tiny error, a spacing of 1.3 millimeters in the wrong position. And this had caused the opticians to polish the mirror to the wrong shape, believing all the while that they were achieving perfection. The error had gone undetected through years of work and multiple layers of quality control. And now, the most expensive scientific instrument ever built was orbiting 340 miles above the Earth with a flawed eye, seeing the universe through a permanent blur. The disappointment was profound, though it was expressed quietly. As such, things often are among those who have devoted their professional lives to a project and must now confront an unexpected and deeply troubling setback. But disappointment was not the end of the story. Not by any measure, for the same ingenuity that had built the telescope in the first place would soon be turned toward finding a way to correct its vision. A solution that would require another mission, another crew, and one of the most remarkable feats of on-orbit repair ever attempted. And so we come now to a quieter chapter, one that begins not with triumph, but with a gentle kind of dismay. The sort of disappointment that settles slowly over a room when something long anticipated does not quite turn out as hoped. The Hubble Space Telescope had launched in April of 1990, carried into orbit aboard the Space Shuttle Discovery. And for a brief moment, it seemed that everything had gone precisely according to plan. The telescope was deployed without incident. Its solar arrays unfurled like delicate wings, catching the sunlight, and the world waited with considerable patience for the first images to arrive. Those promised glimpses of the cosmos rendered in unprecedented clarity. The early signs were encouraging in their way. The telescope was functioning, its systems were communicating with ground control, and the process of bringing the great observatory online proceeded through its careful sequence of checks and calibrations. Engineers and astronomers gathered at the Space Telescope Science Institute in Baltimore and at the Goddard Space Flight Center, watching their monitors and adjusting the telescope's fine guidance sensors, waiting for that moment when the universe would come into focus with a sharpness never before achieved from any instrument built by human hands. But when the first images began to arrive, something was clearly not right. The stars, which should have appeared as tight, ante, brilliant points of light, were instead surrounded by fuzzy halos, their light spreading outward in a soft blur rather than concentrating into the crisp dots that the optical design had promised. At first, there was hope that this was simply a matter of adjustment, that the secondary mirror needed fine-tuning, that some settling of the optical assembly was still taking place in the absence of gravity. Teams worked through the problem methodically, adjusting the spacing between the primary and secondary mirrors by tiny increments, searching for that perfect configuration that would bring the stars into focus. But no amount of adjustment could correct what they were seeing. The blur remained, stubborn and consistent, and as the weeks passed, a troubling realization began to take shape among the engineers and scientists who understood such things. This was not a problem of alignment or adjustment. Something was fundamentally wrong with the optics themselves. The diagnosis, when it finally came, was both precise and devastating. The primary mirror of the Hubble Space Telescope, that magnificent disk of glass that had been polished with such extraordinary care over so many years, had been ground to the wrong shape. The error was almost impossibly small in human terms, a deviation of just 2.2 microns at the outer edge of the mirror, which is to say about 1/50th the width of a single human hair, or roughly 1/25th the thickness of a sheet of ordinary paper. To touch such an error would be to feel nothing at all, for it exists below the threshold of human sensation, in a realm where only light and mathematics can perceive the difference. And yet this tiny error was catastrophic for a telescope designed to see the faintest and most distant objects in the universe. The condition was called spherical aberration, a term from optics that describes what happens when a curved mirror does not bring all incoming light rays to the same focal point. In a properly shaped mirror, light striking the center and light striking the edges all converge at precisely the same spot, creating an image that is sharp across its entire field. But Hubble's mirror was too flat at its edges by that crucial 2.2 microns, and as a result, light from the outer portions of the mirror came to focus at a slightly different point than light from the center. The resulting images were blurred, with perhaps 85% of a star's light spread into that characteristic halo rather than concentrated into the tight point that astronomers had expected. The question that naturally arose was how such an error could have occurred. The mirror had been tested extensively during its fabrication, measured and remeasured with instruments designed to detect deviations far smaller than a human could perceive. Surely such a significant flaw would have been caught somewhere in the long process of grinding and polishing that had occupied the technicians at the Perkin-Elmer Corporation for so many years. The investigation that followed would eventually trace the error to a single measuring device called a null corrector, a specialized optical instrument used to test the shape of the mirror during the polishing process. A null corrector works by shining light onto the mirror and examining the reflected pattern, which will appear uniform only when the mirror's shape is exactly correct. Any deviation from the intended curvature shows up as a distortion in the pattern, alerting the technicians that more polishing is required in certain areas. Perkin-Elmer had built a custom null corrector specifically for testing the Hubble primary mirror, and this device had been assembled with extraordinary precision. Its components positioned using laser measurements and careful calibration. But during that assembly, a small but crucial error had occurred. One of the optical elements within the null corrector, a simple lens called a field lens, had been positioned incorrectly, spaced too far from another component by about 1.3 millimeters. This is roughly the thickness of a coin, an error that would be entirely unremarkable in most circumstances, but which proved fatal for the accuracy of the measurements that followed. With its field lens in the wrong position, the null corrector gave readings that indicated the mirror was perfect when in fact it was not. The polishing technicians, trusting their instrument, continued their work until the null corrector told them they had achieved the ideal shape, not knowing that the ideal they were measuring against was itself flawed. They had polished the mirror to precisely the wrong specification, creating a surface that was exquisitely smooth and beautifully figured, but figured to a shape that was 2.2 microns too flat at its edges. There had been other null correctors, backup instruments that had given slightly different readings, but these discrepancies had been dismissed rather than investigated, a decision that the investigation board would later describe as a significant failure of quality assurance. The backup instruments had, in fact, been correct, but their warnings went unheeded in favor of the primary null corrector that everyone believed to be the most accurate. When the news of the flaw became public, the reaction was swift and, in many quarters, rather unkind. The Hubble Space Telescope had been an expensive project, costing approximately $1.5 billion at that point, and it had been promoted to the public with considerable enthusiasm as a revolutionary instrument that would transform our understanding of the cosmos. To learn that this magnificent machine was now orbiting the Earth with blurred vision, unable to deliver on its promises, struck many observers as an embarrassing failure, perhaps even an inexcusable one. Late-night television hosts made jokes about the telescope, comparing it to various objects of mockery, suggesting that NASA had launched a very expensive piece of defective equipment. Newspaper editorials questioned the competence of the agency and its contractors. The name Hubble itself became something of a punchline for a time, shorthand for government waste and technological hubris. It was an uncomfortable period for everyone involved with the project, particularly for the scientists and engineers who had dedicated years of their lives to building an instrument that was now the subject of public ridicule. And yet, even in those difficult early months, the telescope was not entirely useless. The blur caused by spherical aberration was substantial, but it was also predictable, following a precise mathematical pattern that could be described and, to some extent, corrected through clever processing techniques. At the Space Telescope Science Institute, a team of scientists and computer specialists began developing methods to recover at least some of the clarity that the flawed mirror had stolen. The technique they employed was called deconvolution, a mathematical process that essentially works backward from the blurred image to estimate what the original sharp image must have looked like before the aberration spread the light into halos. If you know exactly how the optical system distorts an image, and in Hubble's case, this was very precisely known, you can apply a kind of mathematical reversal that partially undoes the distortion. It is rather like knowing that someone has smeared a photograph in a very specific way, and using that knowledge to reconstruct what the photograph looked like before the smearing occurred. Deconvolution could not fully restore Hubble's images to their intended sharpness, for some information is genuinely lost when light spreads beyond its proper boundaries, mixing with light from neighboring sources and fading into the background noise. But it could significantly improve the images, pulling details out of the blur and making certain types of observations possible even with the flawed optics. The technique was computationally intensive, requiring considerable processing time for each image, but it demonstrated that the telescope was not a complete loss, that valuable science could still be extracted from its compromised observations. During those early years with the flawed mirror, Hubble did manage to make genuine discoveries, contributions to astronomical knowledge that might otherwise have gone unnoticed. The telescope observed storms in the atmosphere of Saturn, great swirling disturbances in the ringed planet's cloud layers that provided new insights into the dynamics of gas giant atmospheres. It made observations of distant quasars and galaxies, contributing to studies of cosmic structure even though its images lacked the crispness that had been promised. It proved that a space telescope, even one with significant optical problems, could still see things that ground-based observatories could not. But everyone understood that this was not what Hubble had been built to achieve. The telescope had been designed to resolve the finest details of distant galaxies, to measure the distances to remote stars with unprecedented precision, to see back in time toward the earliest epochs of cosmic history. With its blurred vision, it could not fulfill these ambitions. It was a magnificent instrument operating well below its potential, like a concert pianist playing with mittens on, still capable of making music but unable to achieve the virtuosity for which it had been trained. The situation, however, was not hopeless. Indeed, even as the investigation board was documenting the causes of the mirror flaw, and even as the late-night comedians were making their jokes, engineers at NASA were already beginning to consider an extraordinary possibility. The Hubble Space Telescope had been designed from the beginning to be serviced in orbit, its components arranged in modular fashion so that astronauts could replace worn or outdated parts during periodic maintenance visits. This had been considered one of the telescope's great advantages. the ability to be upgraded and repaired over the years rather than simply abandoned when problems arose. And so a daring idea began to take shape. A plan that would have seemed outlandish for almost any other spacecraft, but which Hubble's unique design made conceivable. If the telescope could not be brought back to Earth to have its mirror fixed, perhaps a correction could instead be brought to the telescope. Perhaps astronauts could carry into orbit a device that would compensate for the mirror's flaw, bending the light in just the right way to cancel out the aberration before it reached the cameras and spectrographs. It would be, in effect, a set of corrective lenses for a telescope, glasses for Hubble, installed 340 miles above the Earth's surface by astronauts working in the vacuum of space. It was an audacious concept, a cosmic house call of the most extraordinary kind, requiring new instruments to be designed and built, new procedures to be developed and practiced, and a space shuttle crew to be trained for one of the most complex repair missions ever attempted. The plan offered hope, a path forward from the disappointment and mockery, a chance for redemption both for the telescope and for the agency that had built it. But that is a story that belongs to another chapter, to a later hour of this long, gentle night. For now, let it be enough to know that even in the depths of that difficult period, when Hubble's flawed vision seemed like an insurmountable embarrassment, there were those who refused to accept that the telescope's potential would remain forever unfulfilled. They began their work quietly, methodically, with the patience and determination that great endeavors require, and in doing so, they set the stage for what would become one of the most remarkable repair missions in the history of human spaceflight. In the quiet darkness of early December 1993, the Space Shuttle Endeavour lifted from Kennedy Space Center carrying 7 astronauts and the hopes of an entire scientific community, ascending through the Florida night toward a rendezvous with a telescope that had become, over the preceding 3.5 years, something of a national embarrassment, though also, in truth, a symbol of what might yet be possible when human ingenuity refuses to accept failure as a final answer. The mission designated STS-61 would attempt something that had never been done before. Not merely a repair, but a comprehensive optical correction performed in the unforgiving vacuum of space, where temperatures swing from extreme cold to extreme heat with each orbit, where tools drift away if released for even a moment, and where the nearest help is several hundred kilometers below, utterly unreachable should anything go seriously wrong. The crew selected for this undertaking represented some of the most experienced spacewalkers and shuttle operators that NASA had ever assembled. And their names deserve to be spoken gently here in the darkness, for they carried with them the weight of years of preparation and the knowledge that the world would be watching, though perhaps that pressure, too, became something they learned to set aside as they focused on the meticulous choreography of their tasks. Commander Richard Covey had flown in space 3 times before and brought to the mission a steady calm that would prove essential during the long days ahead, while pilot Kenneth Bowersox, himself a veteran of previous shuttle flights, managed the complex orbital mechanics required to approach and capture the telescope without causing damage to its delicate appendages. The 4 mission specialists who would venture outside the shuttle in alternating pairs had trained for this work for more than a year, practicing their movements in underwater tanks that simulated the weightlessness of orbit, memorizing the location of every handrail and foot restraint on the telescope's exterior. Story Musgrave. At 60 years old, the most senior member of the crew, brought not only vast experience, but also a particular philosophical patience that seemed well suited to work requiring absolute precision under conditions of considerable stress. Jeffrey Hoffman had already conducted spacewalks on previous missions and understood intimately the strange combination of freedom and constraint that comes with working in a pressurized suit, where every movement must be deliberate and every gesture consumes energy. Catherine Thornton, one of the few women to have walked in space by that time, possessed both the technical skill and the careful temperament needed for tasks involving sensitive optical equipment, while Tom Akers, who had performed spacewalks during a previous servicing mission to a different satellite, completed the quartet of specialists who would rotate through the demanding extravehicular activities. When Endeavour reached the telescope on the second day of the mission, the astronauts deployed the shuttle's robotic arm to gently grasp Hubble and lower it into the cargo bay, where it would remain secured while the repair work proceeded. The telescope looked much as it had when deployed 3.5 years earlier, its silver skin reflecting the blue curve of Earth below. Its solar panels extended like wings that had carried it through countless orbits. Though of course the astronauts knew that within that familiar exterior lay optical components that had never quite functioned as intended. The spacewalks began on the 4th day of the mission and continued for 5 consecutive days, an unprecedented sequence of extravehicular activities that totaled approximately 35 hours of work outside the shuttle. Each spacewalk lasted between 6 and 8 hours, during which the alternating pairs of astronauts performed tasks that ranged from replacing gyroscopes and electronic control units to the main event, the installation of corrective optics designed to compensate for the flawed primary mirror that had caused such disappointment upon Hubble's initial activation. The primary optical correction came in the form of a device known as COSTAR, which stands for Corrective Optics Space Telescope Axial Replacement, and which might be thought of, in the most gentle and simplified terms, as a pair of eyeglasses for the telescope, though of course the engineering reality was considerably more complex. Ball Aerospace had designed and built COSTAR under significant time pressure, working backward from the precisely measured error in the primary mirror to create a set of corrective elements that would intercept the light before it reached several of Hubble's scientific instruments. Within the COSTAR housing sat 10 small mirrors, each about the size of a coin, positioned with extraordinary precision so that they would introduce exactly the opposite distortion to that caused by the primary mirror's flawed curvature, the two errors thus cancelling each other out and producing the sharp focus that should have existed from the beginning. Installing COSTAR required first removing one of Hubble's original instruments, the high-speed photometer, which was sacrificed to make room for the corrective optics package. Story Musgrave and Jeffrey Hoffman performed this exchange during one of the spacewalks, carefully disconnecting the photometer and sliding it out of its bay before guiding the new COSTAR unit into position, a process that required patience and precise alignment as the device's connectors engaged with the telescope's internal systems. The astronauts communicated in calm, measured tones with Mission Control in Houston, announcing each step as it was completed, their voices carrying across the distance with a quality that combined focus with a certain understated determination. In addition to CoStar, the mission carried a replacement for the original wide-field and planetary camera, which had been one of the instruments most affected by the spherical aberration. The new camera, designated Wide Field and Planetary Camera 2, or simply WFPC-2, differed from its predecessor in an important way, for its own internal optics had been designed from the start to correct for the primary mirror's error, meaning that it did not require CoStar's intervention to produce properly focused images. This redundancy in the correction approach reflected NASA's determination to restore the telescope's capabilities through multiple pathways, ensuring that even if one method encountered difficulties, the other might still succeed. Catherine Thornton and Tom Akers handled the camera replacement during their spacewalk, removing the original instrument and installing the new one in its place. A procedure that went largely according to plan, though it demanded continuous attention to the alignment of electrical and data connections. The astronauts worked methodically, aware that they were handling equipment worth hundreds of millions of dollars and that any mistake might compromise the mission's success. Yet their movements remained steady, guided by extensive training and the knowledge that haste in such circumstances served no useful purpose. It was during the final days of the spacewalk sequence that an unexpected difficulty arose, one that momentarily elevated tension in mission control and reminded everyone involved of the inherent uncertainties of working in space. The original solar panels that had powered Hubble since its deployment had proven problematic, flexing and vibrating each time the telescope passed from Earth's shadow into sunlight and back again. A thermal response that had caused disturbances in the pointing accuracy of the instruments. The mission had included replacement solar arrays among its cargo, and during one of the spacewalks, the astronauts began the process of removing the old panels and installing the new ones. As they attempted to retract one of the original solar arrays, however, the latches that secured it refused to release properly, resisting the commands sent from the shuttle's controls. For a time, the astronauts and mission controllers worked through the problem, trying different approaches, considering whether the array might need to be jettisoned without full retraction. The minutes passed slowly during this period, each attempted solution meeting with limited success, until finally the decision was made to release the bulky array and allow it to drift away from the telescope, a solution that was not ideal, but that allowed the mission to proceed without expending further precious time. The old panel tumbled gently into the void, its silver surface catching the light as it receded, eventually to descend into Earth's atmosphere and burn up harmlessly. The replacement arrays were then installed successfully, providing the telescope with improved power generation and eliminating the thermal flexing that had troubled the original design. By the time the final spacewalk concluded, the astronauts had accomplished everything they had set out to do and more, replacing or repairing 11 separate components on the telescope and demonstrating that even the most complex orbital repairs were within the reach of careful planning and skilled execution. On December 9th, the shuttle's robotic arm lifted the refurbished telescope out of the cargo bay and released it back into free flight, where it resumed its patient orbit around Earth, its systems gradually coming back online as engineers on the ground verified the success of each repair. The weeks that followed were a time of calibration and testing, as the telescope's instruments were focused and aligned, their sensitivity checked against known celestial targets. The astronomers who had waited so long for this moment understood that the proof of the mission's success would come not in engineering reports or status updates, but in the quality of the images the telescope produced. And so they waited with quiet anticipation for the first corrected observations to be processed and released. On January 13th, 1994, NASA held a press conference to unveil the results. And what the world saw in those images was nothing short of a transformation. Where once stars had appeared as fuzzy blobs surrounded by halos of scattered light, they now presented themselves as sharp pinpoints, clean and precise against the blackness of space. The corrective optics had worked exactly as designed, compensating for the error in the primary mirror and delivering the image quality that had been promised at the telescope's inception. Side-by-side comparisons showed the difference with unmistakable clarity. Before and after images that told a story of failure, acknowledged and then overcome through persistent effort. For the scientific community, the corrected images represented far more than a public relations recovery, though that aspect certainly mattered to the agencies and institutions that had invested so much in the telescope's success. What the sharp new images meant, fundamentally, was that Hubble could now do the science it had been built to do, peering deeper into the universe than any previous telescope, resolving details that had remained forever blurred to ground-based instruments hampered by Earth's turbulent atmosphere. Galaxies that had appeared as smudges of light revealed their spiral arms and dust lanes. Stars in crowded fields could be distinguished from one another for the first time. The planets of our own solar system showed surface features with unprecedented sharpness. In a sense, the telescope had been reborn, transformed from an object of disappointment into an instrument of discovery. And the years that followed would amply demonstrate just how valuable that transformation had been. Yet, in this quiet moment, as we rest here in the gentle darkness, it is perhaps enough to hold in mind the image of those astronauts working patiently against the backdrop of Earth, installing small mirrors no larger than coins, adjusting the prescription through which an entire civilization would come to see the cosmos more clearly. The work was methodical and unglamorous, a series of careful steps performed one after another over 5 long days, and when it was done, the universe that had always been there waiting came at last into focus. In the autumn of 1995, a man named Robert Williams found himself in possession of something rather unusual, which was a certain amount of time that belonged entirely to him. Robert Williams was the director of the Space Telescope Science Institute in Baltimore, Maryland, and in that role he had inherited a quiet tradition that granted the director a small portion of Hubble's observing schedule to use as he saw fit, without the need for committee approval or peer review or any of the ordinary processes that governed how the telescope spent its hours. This was called director's discretionary time, and it amounted to perhaps 10% of the telescope's annual schedule. And Williams had been thinking for some while about how he might use this precious allocation in a way that would be genuinely meaningful, even if others could not immediately see why. The Hubble Space Telescope had been in orbit for 5 years by then, circling the Earth every 97 minutes at an altitude of roughly 540 kilometers. and it had already proven itself capable of extraordinary things. The initial disappointment of its flawed mirror had been corrected in 1993, when astronauts installed new optics that allowed the telescope to see with the clarity it had always promised. And in the years since that repair mission, Hubble had returned images of nebulae and galaxies and stellar nurseries that had captivated both scientists and the general public alike. There was tremendous demand for time on the telescope, with astronomers from around the world submitting proposals for observations of specific objects, known phenomena, targets of established interest. The competition was fierce, and every hour of Hubble's time was considered precious beyond ordinary measure. So when Robert Williams began to discuss his idea with colleagues, the response he received was not enthusiasm, but rather something closer to concern, and in some cases outright opposition. What Williams wanted to do was point the most powerful optical telescope ever placed in space at a patch of sky where there appeared to be nothing at all. He had selected a region near the handle of the Big Dipper, that familiar asterism in the constellation Ursa Major visible from the northern hemisphere. And in this region, the sky appeared dark and empty to ground-based telescopes. There were no bright stars in the field, known galaxies of particular interest, no nebulae or clusters or any of the usual targets that astronomers competed so fiercely to observe. To many of his colleagues, the proposal seemed at best eccentric and at worst a reckless waste of an irreplaceable resource. Some worried that Williams was about to squander hundreds of orbits of telescope time on an image of nothing, that the result would be a very expensive photograph of empty space, that the scientific community would rightly criticize the decision, and that the credibility of the institute itself might suffer as a consequence. The patch of sky Williams had chosen was almost impossibly small. If you were to hold a single grain of sand at arm's length against the night sky, that grain would cover approximately the same angular area that Williams intended to observe, which was about 1/24 millionth of the entire sky. It was a tiny window into the darkness, and the darkness, to all appearances, contained nothing of interest. The region had been selected precisely because it was boring, because it was empty, because it was as close to a blank canvas as the universe seemed to offer. Williams reasoned that if Hubble stared at this emptiness long enough, gathering photons with patient persistence over many consecutive days, the telescope might reveal what the darkness actually contained. He suspected that the void was not truly void at all, that what appeared to be nothing might in fact be something very distant and very faint, that the blackness between the stars might be crowded with objects so remote that their light had been stretched and dimmed almost beyond detection. On the 18th of December, 1995, the observation began. Hubble turned its gaze toward that small and seemingly insignificant patch of sky, and it began to collect light. The telescope could not simply take one long exposure, because the logistics of orbital mechanics and the need to avoid various sources of interference made that impossible. Instead, the observation was broken into many separate exposures, each one lasting anywhere from 15 to 40 minutes, and these exposures accumulated over the course of 10 consecutive days. The telescope would capture an image, then swing away to observe other targets as required by the schedule, then return to the same patch of sky and capture another exposure, building up the data gradually, frame by frame, orbit by orbit, By the time the observation was complete in early January of 1996, Hubble had taken 342 separate exposures of that tiny region, totaling more than 100 hours of observation time. The images were captured through multiple filters, sampling different wavelengths of light, so that the final result could be assembled as a color composite that revealed not only the presence of objects, but something of their character as well. The data was transmitted from the telescope to the ground stations and then to the Space Telescope Science Institute, where it was processed and combined and calibrated. The individual exposures were stacked together, each one contributing its small harvest of photons to the growing whole. And as the processing continued, the image began to emerge. What had appeared to be darkness was not darkness at all. The tiny patch of sky, that grain of sand window into the void, was filled with galaxies. Not dozens, not hundreds, but nearly 3,000 distinct galaxies became visible in that single small frame. Each one a vast collection of billions of stars. Each one a separate island universe suspended in the depths of space. Some were spirals, their arms pinwheeling gracefully, while others were ellipticals, smooth and golden and ancient. Some were irregular, disturbed perhaps by gravitational encounters with neighbors. Some were large and relatively nearby, while others were small and impossibly distant. Their light having traveled across such immense reaches of space that it had been stretched by the expansion of the universe into longer, redder wavelengths. The most distant of these galaxies had emitted their light when the universe was very young, perhaps only 1 billion years or so after the beginning of time itself. That light had been traveling through space for roughly 12 billion years before it finally arrived at Hubble's mirror, which meant that the telescope was seeing these galaxies not as they existed in the present day, but as they had existed in the distant past, when they were newly formed, when the universe itself was still in its youth. The image was not merely a photograph of a region of space, but a kind of time machine, revealing the history of cosmic evolution in a single frame. The older and more distant galaxies appeared different from the younger and nearer ones, showing the processes of galaxy formation and growth in ways that had never before been observed. The result was called the Hubble Deep Field, and when it was released to the scientific community and to the public, it changed the way that many people thought about the universe. The implications were profound, and yet, in the manner of all truly deep discoveries, they were also strangely calming, for the image revealed that the universe was fuller and richer than anyone had dared to imagine. If a random and apparently empty patch of sky contained nearly 3,000 galaxies, then the total number of galaxies in the observable universe must be immense beyond easy comprehension. Subsequent estimates suggested that there might be hundreds of billions of galaxies scattered throughout the cosmos, each one containing hundreds of billions of stars, each star potentially circled by planets, each planet a world unto itself. The emptiness had never been empty. The darkness had always been full of light, waiting only for an instrument patient enough to gather it. Robert Williams and his colleagues had taken what many considered an unjustifiable risk, and they had been rewarded with one of the most important astronomical images ever captured. The scientists who had questioned the decision now recognized its wisdom, and the Hubble Deep Field became one of the most studied and most referenced images in the history of astronomy. It demonstrated the value of looking where others assumed there was nothing to see, of investing precious resources in observations that might yield nothing, but might also yield everything. The success of the original Hubble Deep Field led naturally to further observations of the same kind. In 1998, astronomers conducted a similar observation in the southern hemisphere sky, pointing Hubble at another apparently empty patch in the constellation, Tucana, and collecting data over a period of 10 days. This observation was called the Hubble Deep Field South, and its results were consistent with those of the original Northern Deep Field, revealing once again that the darkness was filled with galaxies, that the universe was uniformly populated with these vast stellar islands, no matter which direction one chose to look. The two deep fields together suggested that the distribution of galaxies was roughly homogeneous on the largest scales, that the universe had no preferred direction, that wherever one pointed a sufficiently sensitive telescope and waited long enough, one would find the same astonishing abundance of distant worlds. Then, in 2004, astronomers conducted an even more ambitious observation, pointing Hubble at a region of sky in the constellation Fornax and collecting data over a total of 11.3 days of exposure time. This observation, called the Hubble Ultra Deep Field, gathered light from objects even fainter and more distant than those seen in the original deep fields. The resulting image revealed approximately 10,000 galaxies in a patch of sky again, no larger than a grain of sand, held at arm's length. And some of these galaxies were so remote that their light had been traveling for more than 13 billion years, meaning that they were seen as they existed when the universe was only a few 100 million years old. These were among the first galaxies ever to form, primitive assemblages of stars coalescing out of the primordial gas that filled the young cosmos. And their light had been journeying across the expanding universe for nearly the entire history of time. Each of these deep field observations confirmed and extended the lessons of the original. The universe is vast beyond human intuition, populated with structures so numerous that counting them requires estimates and extrapolations rather than direct enumeration. The spaces between the stars, which appear so dark and empty to the unaided eye, are in fact corridors through which light travels from unfathomably distant sources, each photon a messenger carrying news from another place and another time. The deep fields revealed that the night sky is not a dome but a depth, not a ceiling but an ocean, and that the darkness is merely a function of distance and the limitations of our vision rather than an absence of things to see. The astronomers who conduct these observations do so with patience and care, planning each exposure, calibrating each instrument, processing each fragment of data with meticulous attention. The work is slow and methodical, requiring weeks and months of preparation before the observations can even begin, and then further weeks and months of analysis before the results can be understood and shared. It is not dramatic work in the conventional sense, but it is profound work, peeling back layer after layer of cosmic obscurity to reveal what lies beyond. And what lies beyond, as the deep fields have shown, is always more than we expected. More galaxies, more stars, more light, more history, more universe. So, if you find yourself looking up at the night sky on a clear evening, And if you notice the darkness between the stars, you might allow yourself to imagine what that darkness truly contains. In every direction, in every apparently empty patch of sky, there are galaxies beyond counting, their light streaming toward us across billions of years. And all we need to see them is a patient instrument and enough time. The universe, it turns out, has been waiting for us to look. And when we finally did, we found that the emptiness was never empty at all. That every darkness was secretly crowded with island universes, each one a home to countless suns. Each sun perhaps a home to worlds we have not yet discovered and may never see. And that thought, rather than being overwhelming, might instead be quietly reassuring, for it suggests that the cosmos is a generous place, filled with more wonders than we could ever exhaust, and that there will always be something new waiting in the darkness, patient and unhurried, for whenever we are ready to find it. On the first day of April in 1995, the Hubble Space Telescope turned its gaze toward a small region of sky in the constellation Serpens, and what it captured there would become perhaps the most recognizable astronomical image ever created, a photograph so striking and so deeply evocative that it would find its way onto posters in children's bedrooms, onto the covers of scientific journals, and into the quiet corners of human imagination where we keep our most profound wonderings about the universe and our place within it. The image came to be known as the Pillars of Creation, and, though that name might sound rather grand, it is in fact a gentle and accurate description of what we see. For these towering columns of interstellar gas and dust are indeed the birthplaces of stars. The quiet nurseries where new suns slowly gather themselves into being across timescales that make our human concerns seem wonderfully small and restful. The astronomers responsible for this observation were Jeff Hester and Paul Scowen, both working at Arizona State University at the time, and they had proposed using Hubble to study a region within the Eagle Nebula, which is also catalogued rather more plainly as Messier 16. This nebula lies approximately 6,500 light-years from Earth, which means that the light captured by Hubble on that April day had been traveling through the darkness of space since roughly 4,500 years before the Common Era, when humans on Earth were just beginning to develop the earliest forms of writing, entirely unaware that their distant descendants would one day build a telescope and send it beyond the atmosphere to catch these ancient photons. The Eagle Nebula itself is a vast cloud of hydrogen gas, the most abundant element in the universe, and within this cloud there are regions of slightly greater density where gravity has begun its patient work of pulling matter together, the first tentative steps in the formation of new stars. The pillars themselves are truly enormous structures, stretching roughly 4 to 5 light-years from their bases to their tips, which is to say that if you were somehow able to travel at the speed of light, it would take you 4 to 5 years simply to traverse the length of one of these columns. To put this in perhaps more restful terms, the distance from our own Sun to the nearest neighboring star, Proxima Centauri, is approximately 4 light-years, so each of these pillars is comparable in length to the gulf between our solar system and its closest stellar neighbor. And yet, despite their immense size, the pillars appear in Hubble's image with such clarity and such delicate detail that one might almost imagine reaching out to touch them, to trace the sculpted edges where the gas meets the surrounding void. The pillars owe their distinctive shapes to a process that astronomers describe with characteristically gentle understatement as photoevibration. Within the Eagle Nebula, there are young, massive stars that burn with tremendous intensity, and the ultraviolet radiation streaming outward from these stars gradually erodes the surrounding gas clouds, much as a gentle but persistent wind might slowly wear away a sandstone cliff over countless millennia. The pillars exist because the gas within them is slightly denser than the surrounding material, and this density provides a measure of protection against the stellar radiation, allowing these columns to persist even as the less dense gas around them is swept away. At the tips of the pillars, where the erosion is most intense, small knots of even denser gas have been revealed, and these knots have been given the rather endearing name of evaporating gaseous globules, or EGGs for short. Within some of these EGGs, the concentration of matter has become sufficient for gravity to take hold in earnest, and embryonic stars are slowly forming, gathering mass and growing warmer as they prepare for the moment. Still, perhaps hundreds of thousands of years distant, when nuclear fusion will ignite in their cores and they will begin to shine with their own light. The image captured by Hester and Scowen was not a single photograph in the way we might ordinarily understand the term, but rather a composite created from 32 separate observations made through different filters, each isolating the light emitted by particular elements within the nebula. The greenish hues in the image correspond to hydrogen, the most prevalent component, while the red tones reveal the presence of singly ionized sulfur, and the blue regions indicate doubly ionized oxygen. This technique of assigning colors to different elemental emissions allows astronomers to study the chemical composition and physical conditions within the nebula. But it also produces images of remarkable and unexpected beauty, revealing structures and gradients that would be invisible to the unaided human eye, even if we could somehow transport ourselves to the Eagle Nebula and gaze upon it directly. In the years following the release of the Pillars of Creation image, Hubble continued its patient survey of the cosmic nurseries and stellar graveyards scattered throughout our galaxy and beyond. And in doing so, it captured a succession of images that expanded our visual vocabulary for describing the life cycles of stars. In 2010, the telescope turned its attention to the Carina Nebula, another vast star-forming region located approximately 7,500 light-years from Earth. And there, it photographed a structure that came to be known informally as Mystic Mountain. This towering column of gas and dust rises some 3 light-years above the surrounding nebular plane, its surface sculpted by the same forces of stellar radiation that shaped the pillars in the Eagle Nebula. And at its summit, thin jets of gas stream outward from newly forming stars, hidden within the dense material. The first visible signs of stellar infancy emerging from the obscuring dust. The Mystic Mountain image possesses a quality that is perhaps even more sculptural than the Pillars of Creation, with intricate ridges and valleys carved into its surface, and wisps of gas trailing away like delicate pennants in an unfelt breeze. The colors in this image, rendered through the same technique of mapping elemental emissions to visible hues, range from deep blues and cyans near the base to warm ambers and browns toward the summit, creating an impression of depth and dimensionality that invites the eye to wander slowly across the frame. discovering new details with each unhurried examination. But Hubble's imagery has not been confined to the birthplaces of stars, for the telescope has also captured with equal tenderness the quiet endings of stellar lives, the graceful exhalations of aging suns as they shed their outer layers into space and leave behind only the small, dense remnants we call white dwarfs. Among the most celebrated of these images is the Helix Nebula, located approximately 700 light-years from Earth in the constellation Aquarius, which has sometimes been called the Eye of God, though this name was bestowed not by the astronomers who studied it, but by the public who found in its appearance something startlingly, almost disturbingly evocative. The nebula is what astronomers call a planetary nebula, though this term is somewhat misleading since it has nothing whatsoever to do with planets. The name dates from the 18th century, when early observers noted that these objects appeared through their telescopes as small, round, somewhat fuzzy disks, not unlike the planets of our solar system, and the name persisted even after we came to understand their true nature. The Helix Nebula was created by a star not terribly different from our own Sun, a star that exhausted the hydrogen fuel in its core and began to burn helium instead, swelling in the process to become a red giant before eventually shedding its outer layers in a series of gentle pulsations. The gas ejected by the dying star has been expanding outward for roughly 10,000 years, and it now forms a great bubble nearly 3 light-years across, with the small, hot remnant of the original star glowing at its center. In Hubble's image, the nebula appears as a vast cosmic iris, with concentric rings of glowing gas in shades of blue and red surrounding a central pupil of deeper darkness. And the resemblance to an eye is so striking that it is difficult not to feel, at least for a moment, that the universe is gazing back at us with something like recognition. Another of Hubble's most striking images of stellar death is the Butterfly Nebula, formerly catalogued as NGC 63022, which lies approximately 3,800 light-years from Earth in the constellation Scorpius. This nebula was created by a star considerably more massive than the Helix Nebula's progenitor, and its death throes were correspondingly more dramatic, though the word dramatic perhaps conveys too much urgency for our present purposes. The dying star ejected its outer layers not in a gentle spherical expansion, but in 2 great lobes extending in opposite directions, creating the distinctive butterfly or hourglass shape that gives the nebula its common name. The gas in these lobes is moving outward at velocities approaching 600,000 miles per hour, which seems almost impossibly fast until one remembers that these events unfold across thousands of years, and that the nebula we observe today is merely a single frame in a transformation that began long before human civilization existed and will continue long after any individual observer has returned to sleep. At the center of the Butterfly Nebula lies one of the hottest stars known, with a surface temperature of approximately 200,000 degrees Celsius, more than 30 times hotter than the surface of our own Sun. This intense heat causes the surrounding gas to fluoresce brilliantly, producing the complex palette of colors visible in Hubble's image, from the deep reds of nitrogen to the blues and purples of ionized oxygen. The intricate structures within the lobes, the wisps and filaments, and delicate lacework of glowing gas, reveal the complex processes by which the dying star shed its outer layers. Processes that we are only beginning to understand despite decades of careful observation and theoretical modeling. What these images accomplished, beyond their purely scientific value, was a transformation in how the general public understood and related to the distant processes of stellar birth and death. Before Hubble, these phenomena were largely abstract concepts, described in textbooks with diagrams and equations, but rarely glimpsed with the kind of immediacy that Hubble provided. The pillars of creation and their kindred images made visceral what had previously been merely intellectual, allowing anyone who gazed upon them to feel, rather than simply know, that stars are born and stars die, that the universe is engaged in a continuous process of creation and dissolution that operates according to principles we can understand, even if we cannot fully comprehend the scales of time and space involved. In 2022, too, the James Webb Space Telescope captured its own images of the pillars of creation, using its infrared instruments to peer through the dust that remains opaque to Hubble's visible light cameras. And these new images revealed even more detail within the pillars, including the embryonic stars hidden within the EGGs and the complex internal structures of the columns themselves. But rather than replacing Hubble's iconic image, the Webb observations served to complement and enrich it, providing additional layers of information that deepen our understanding without diminishing the wonder that the original image inspired. The two telescopes, working in concert across the electromagnetic spectrum, offer us something like stereoscopic vision, allowing us to perceive depths and details that neither instrument alone could reveal. And so, as you settle more deeply into rest, perhaps you might carry with you the thought of those distant pillars, standing patiently in their nebula 6,500 light-years away, slowly giving birth to new stars, even as the radiation of older stars gradually erodes them into ever more delicate and beautiful shapes. The processes that sculpt them are patient beyond imagining, and the light that brings us word of their existence has traveled through the darkness for millennia before reaching our telescopes and our eyes. There is something deeply restful in contemplating such vast timescales, in recognizing that the universe proceeds about its business of creation and dissolution with a steadiness that makes our own concerns seem fleeting and small, not in a way that diminishes us, but in a way that invites us to release our grip on wakefulness and trust that the cosmos will continue its gentle work while we sleep. In the quiet corridors of astronomical research during the middle years of the 1990s, two separate groups of scientists were engaged in what they believed would be a relatively straightforward measurement, a kind of cosmic accounting exercise that would tell us something we thought we already knew about how the universe would end. They were not expecting to overturn decades of cosmological thinking, and they were certainly not expecting to discover that the universe was hiding something vast and strange, something that would eventually be given the name dark energy, a name that captures both our ignorance and our wonder in equal measure. These two teams, working independently and sometimes in friendly competition, would use the Hubble Space Telescope as one of their essential instruments, and what they found would earn them the highest honor in physics and would change forever the way we understand the fate of everything that exists. The first of these groups was called the Supernova Cosmology Project, and it was led by a physicist named Saul Perlmutter, who worked at the Lawrence Berkeley National Laboratory in California, a sprawling research facility nestled in the hills above the University of California campus. Perlmutter had begun his work in the late 1980s, and he had spent years developing techniques for finding and measuring a particular type of stellar explosion, the kind of explosion that astronomers call a Type Ia supernova. His team grew slowly, gathering researchers from institutions around the world, and by the middle of the 1990s, they had developed methods that allowed them to discover dozens of these distant explosions, far more than anyone had found before. The work was painstaking and required careful coordination between ground-based telescopes, which would first detect the supernovae, and space-based instruments like Hubble, which could provide the precise measurements needed to determine just how far away these explosions were and how fast the universe was carrying them away from us. The second group was called the High Z Supernova Search Team, and it was led by Brian Schmidt, a young astronomer originally from Montana who had moved to Australia to work at the Australian National University in Canberra, and by Adam Rees, a postdoctoral researcher at the University of California, Berkeley, who would later move to Johns Hopkins University. The letter Z in their name referred to redshift, the stretching of light that occurs when an object is moving away from us, and high Z meant they were looking at supernovae with large redshifts, which is to say, supernovae that were very far away indeed, so far that their light had been traveling for billions of years before reaching our telescopes. This team, like Perlmutter's group, was hunting the same cosmic quarry, trying to measure something called the deceleration parameter, a number that would tell us how quickly the expansion of the universe was slowing down. You see, by the 1990s, it was widely accepted that the universe had begun in a hot, dense state some 14 billion years ago, and that it had been expanding ever since, with galaxies moving apart from one another like raisins in a rising loaf of bread. What was not known with precision was whether this expansion would continue forever, gradually slowing but never quite stopping, or whether there was enough matter in the universe to eventually halt the expansion and perhaps even reverse it, pulling everything back together in a kind of mirror image of the original explosion. To answer this question, astronomers needed to measure how the expansion rate had changed over cosmic time. And to do that, they needed to find objects at great distances whose brightness they could trust, objects that would serve as what astronomers call standard candles. A standard candle is simply an object whose intrinsic brightness, the amount of light it actually produces, is known or can be calculated. If you know how bright something truly is, and you measure how bright it appears to be from where you stand, you can work out how far away it must be, because light dims with distance in a predictable way, following what is called the inverse square law. The challenge, of course, is finding objects whose true brightness you can trust, objects that do not vary unpredictably from one example to another. For many years, astronomers had used various objects as standard candles, including certain types of variable stars called Sepiites. But to look back billions of years into the past, to see the universe as it was when it was much younger, they needed something brighter, something that could be seen across unimaginable distances, and that something was the Type Ia supernova. A Type Ia supernova occurs in a binary star system, a system where two stars orbit around one another, locked in a gravitational dance that can last for millions or billions of years. In these particular systems, one of the stars is a white dwarf, which is the dense remnant core of a star that has exhausted its nuclear fuel and collapsed down to roughly the size of the Earth, even though it may contain a mass comparable to our Sun. The white dwarf slowly pulls material from its companion star, gas that spirals down onto the surface of the dwarf and accumulates there, adding to its mass bit by bit. When the white dwarf reaches a critical mass, about 1.4 times the mass of our Sun, a threshold known as the Chandrasekhar limit after the Indian-American astrophysicist who calculated it, something remarkable happens. The pressure and temperature at the core become so extreme that carbon and oxygen begin to fuse in a runaway nuclear reaction, and the entire star explodes with a brightness that can briefly outshine an entire galaxy. Because all Type Ia supernovae explode at approximately the same mass, they all release approximately the same amount of energy, and they all reach approximately the same peak brightness, which makes them extraordinarily useful as standard candles. Of course, there are small variations from one supernova to another, but astronomers have developed techniques to account for these variations by studying how the brightness changes over time, the shape of the light curve as they call it, and by making careful observations at multiple wavelengths. With these corrections applied, Type Ia supernovae become reliable distance markers, cosmic beacons that can be seen across billions of light-years and that tell us, by their apparent dimness, just how far away they are. Both teams, the Supernova Cosmology Project and the High Z Supernova Search Team, were using these exploding stars to measure the history of cosmic expansion. The idea was simple in principle, though extraordinarily difficult in practice. If you measure supernovae at various distances, you are effectively looking back in time, because light from more distant explosions takes longer to reach us. A supernova 1 billion light-years away shows us the universe as it was 1 billion years ago, and a supernova 8 billion light-years away shows us the universe as it was 8 billion years ago. By comparing how fast the universe was expanding at different times in the past, you can determine whether the expansion has been slowing down, as everyone expected, or perhaps staying steady, or behaving in some other way entirely. The expectation, shared by nearly all cosmologists at the time, was that the expansion would be decelerating, slowing down over time. This was because gravity, the attractive force between all matter, should be working against the expansion, pulling galaxies back toward one another and gradually reducing the rate at which they fly apart. The only question, or so it seemed, was how much deceleration there was, which would tell us whether the universe would expand forever or eventually collapse. The teams set out to measure this deceleration parameter, expecting to find a positive number, a number indicating that the cosmic brakes were being applied, gently but persistently, across the eons. The Hubble Space Telescope played a crucial role in this work, particularly for the most distant supernovae, the ones that were too faint and too far away to be measured accurately from the ground. Hubble's position above the atmosphere meant that it could make precise photometric measurements without the blurring and absorption that ground-based telescopes had to contend with, and its cameras could capture the faint glow of supernovae that had exploded when the universe was less than half its present age. The teams would discover new supernovae using ground-based telescopes, which could survey large areas of the sky relatively quickly, and then they would apply for observation time on Hubble to make the detailed follow-up measurements that would reveal the true brightness and distance of each explosion. As the data accumulated through the mid and late 1990s, something puzzling began to emerge. The distant supernovae, the ones that were 7 or 8 billion light-years away, appeared to be dimmer than they should be. Not by a dramatic amount, not glaringly, obviously wrong, but consistently and persistently fainter than the calculations predicted. If the universe were decelerating as expected, these ancient explosions should have appeared at a certain brightness. But they were about 25% dimmer than that, which meant, according to the inverse square law, that they were farther away than they should have been. The light had traveled a greater distance than a decelerating universe would have allowed. At first, both teams assumed there must be some error, some systematic problem with their measurements or their analysis. Perhaps the distant supernovae were intrinsically different from nearby ones. Perhaps they were being dimmed by intergalactic dust in ways that had not been accounted for. Perhaps there was some subtle flaw in the calibration of the instruments. The researchers checked and rechecked their data, looked for every possible source of error, and tried to make the puzzle go away. But it would not go away. The data stubbornly insisted that something unexpected was happening, something that required a dramatic rethinking of our cosmic model. The conclusion, reached independently by both teams and published in 1998, was startling. The universe was not decelerating at all. Instead, it was accelerating. The expansion was speeding up, not slowing down, as though some invisible force were pushing the galaxies apart, working against gravity and winning. This was not a small effect, a minor correction to the standard model, but a fundamental revision of our understanding of cosmic dynamics. Something was driving the expansion, something that had no obvious explanation in the physics that was known at the time. The name given to this mysterious phenomenon was dark energy, a term chosen partly by analogy with dark matter, the equally mysterious, invisible substance that holds galaxies together, and partly because it captured the profound ignorance that surrounded this discovery. Dark energy is not dark in the sense of being black or unlit, but rather in the sense of being unknown, hidden from our understanding, detectable only through its gravitational effects on the largest scales. It appears to act as a kind of repulsive force, or more precisely, as a negative pressure that pervades all of space and causes the expansion of the universe to accelerate rather than slow down. The more space there is, the more dark energy there is, and so, as the universe expands and space itself grows larger, dark energy becomes ever more dominant, pushing the galaxies apart faster and faster. Current observations suggest that dark energy accounts for approximately 68% of the total energy content of the universe, which makes it by far the dominant component of cosmic reality. Ordinary matter, the kind of matter that makes up stars and planets and people, accounts for less than 5%, and dark matter makes up about 27%. This means that everything we can see, everything that emits or reflects light, everything that astronomers have studied for centuries, constitutes only a small fraction of what exists. The universe is mostly made of something we do not understand, something that is driving it to expand ever faster into the darkness. In the year 2011, the Nobel Prize in Physics was awarded jointly to Saul Perlmutter, Brian Schmidt, and Adam Rees for the discovery of the accelerating expansion of the universe through observations of distant supernovae. The award recognized not only the significance of the discovery itself, but also the careful and rigorous work that both teams had done to ensure that their startling conclusion was correct. The Hubble Space Telescope, which had provided essential observations for this work, had once again demonstrated its value as an instrument of fundamental discovery, a machine for revealing truths about the cosmos that we could not have anticipated. What began as a straightforward measurement of cosmic deceleration had ended with the revelation that the universe was stranger than anyone had imagined. The fate of everything, all the galaxies and stars and planets, depended on something we could not see and did not understand, a force that would continue to push the cosmos apart until the distant galaxies faded beyond the horizon of observation, carrying their light away faster than it could ever reach us. It was a discovery that inspired wonder and humility in equal measure, a reminder that the universe does not arrange itself according to our expectations, and that the most profound truths are often the ones we stumble upon by accident, while looking for something else entirely. And now we come to something rather curious, a puzzle that sits quietly at the heart of modern cosmology, waiting patiently to be understood. It concerns a number, a single measurement that describes how quickly our universe is expanding, and the peculiar fact that when scientists measure this number in different ways, they arrive at answers that do not quite agree. This disagreement has come to be known as the Hubble tension, and it represents one of the most significant unresolved questions in our understanding of the cosmos, a gentle mystery that Hubble has helped illuminate, even if it cannot yet provide the final answer. To understand this puzzle, we must first understand what the Hubble constant is, and why it matters so much to astronomers who study the large-scale structure of everything that exists. The Hubble constant, often written as h0 or h0, is a number that tells us the rate at which the universe is currently expanding. It describes how fast distant galaxies appear to be moving away from us, and it does so in a rather specific way, measuring the velocity of recession in kilometers per second for every megaparsec of distance between us and those faraway places. A megaparsec, you may recall, is a unit of astronomical distance equal to about 3.26 million light-years, a span so vast that it contains countless stars and perhaps countless worlds, stretching across the darkness in quantities too large for the mind to hold comfortably. When Edwin Hubble first discovered that the universe was expanding back in the late 1920s, he attempted to measure this rate of expansion, and his early estimates were rather imprecise, as one might expect from the technology of that era. But in the decades since, astronomers have refined their techniques enormously, developing ever more sophisticated methods for measuring cosmic distances and velocities. And the Hubble Space Telescope has played a central role in these efforts, providing the clear and steady observations necessary to push our measurements toward greater and greater precision. And it is precisely this precision that has revealed the puzzle. Because when you measure something very carefully, you begin to notice discrepancies that cruder instruments might have missed. One of the leading efforts to measure the Hubble constant using the Hubble Space Telescope has been conducted by a team led by Adam Rees, an astronomer who shared the Nobel Prize in Physics for the discovery of dark energy and the accelerating expansion of the universe. Rees and his colleagues have spent many years working on what they call the SH0 project, which stands for supernova H0 for the equation of state, a name that reflects the technical nature of their work and the specific phenomena they study. The approach they have taken involves measuring distances to galaxies using a particular type of star called a Cepheid variable, those rhythmically pulsing stars we encountered earlier, whose brightness waxes and wanes in predictable patterns that reveal their intrinsic luminosity. The SH0 team used the Hubble Space Telescope to observe Cepheid variable stars in 42 different galaxies, a substantial sample that allows for statistical confidence in their results. By measuring the apparent brightness of these Cepheids and comparing it to their known intrinsic brightness, they could calculate the distances to each galaxy with considerable accuracy. They then combined these distance measurements with observations of Type Ia supernovae, those standardizable explosions we discussed before, to extend their distance ladder even further into the cosmos. And by examining how quickly these galaxies appeared to be receding from us, as revealed by the redshift of their light, they calculated the current rate of cosmic expansion with what they believed to be remarkable precision. The number they arrived at, after years of careful observation and analysis, was approximately 73 kilometers per second per megaparsec. This means that for every megaparsec of distance between us and a far-off galaxy, that galaxy appears to be receding from us at an additional 73 kilometers per second, a rate that accumulates across the vast expanses of intergalactic space until the most distant galaxies are rushing away from us at substantial fractions of the speed of light itself. This measurement has been refined over multiple iterations of the SH0 project, and each refinement has served to increase the team's confidence in their result, while also slightly adjusting the precise value as more data becomes available and systematic errors are better understood. But here is where the puzzle emerges, softly and persistently, refusing to go away no matter how carefully the measurements are checked. There is another way to determine the Hubble constant, one that does not rely on observing nearby stars and galaxies at all, but instead looks back to the very early universe, to a time long before any galaxies had formed, when the cosmos was filled with a hot, dense plasma that eventually cooled and released a faint glow of light that still permeates all of space today. This ancient light is called the cosmic microwave background, and it was released approximately 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and for light to travel freely without being constantly scattered by charged particles. The cosmic microwave background has been studied in exquisite detail by several space missions, most notably the Planck satellite, which was launched by the European Space Agency and operated from 2009 to 2013. Planck mapped the tiny temperature variations in this ancient light with extraordinary precision, and from these measurements, cosmologists were able to infer a great deal about the early universe, including its composition, its geometry, and the conditions that prevailed when the cosmos was young. By combining these observations with our best theoretical models of how the universe has evolved over the past 13.8 billion years, scientists can calculate what the Hubble constant should be today, based on what the universe looked like in its infancy and how it ought to have expanded since then. The number that emerges from this analysis, from the Planck satellite's observations of the cosmic microwave background, is approximately 67.4 kilometers per second per megaparsec. This is noticeably smaller than the value measured by the SH0E's team using Cepheid variables and supernovae, and therein lies the tension. The difference between 73 and 67.4 may not seem enormous in everyday terms, but in the context of precision cosmology, where measurements are now accurate to within a few percent, this discrepancy of roughly 9% is deeply significant. These two approaches should, according to our current understanding of physics, yield the same answer, because they are both measuring the same quantity, the rate at which the universe is expanding right now. And yet, they do not agree. What makes this discrepancy so troubling and so fascinating is that it is almost certainly not the result of simple measurement error or statistical fluctuation. Both teams have checked and rechecked their work, looking for sources of systematic error that might explain the difference, and both have arrived at results they believe to be robust. When statisticians analyze the probability that this disagreement is merely a chance occurrence, the kind of random variation that might arise from the inherent uncertainties in any measurement, they find that the odds are vanishingly small, approximately 1 in a million, or perhaps even less. This means that something more fundamental is almost certainly at play, that either one of the measurements contains an unrecognized error, or, perhaps more excitingly, that our understanding of the universe itself is incomplete in some important way. Astronomers and cosmologists have proposed various explanations for the Hubble tension, each representing a different way in which our current models might be missing something essential. One possibility involves what is called early dark energy, a form of energy that may have been present in the early universe, shortly after the Big Bang, and that would have affected the rate of cosmic expansion in ways not accounted for by our standard models. This early dark energy would have been different from the dark energy that dominates the universe today, which causes expansion to accelerate, and its effects would have been most significant during a particular period of cosmic history, altering the relationship between the early universe observed by Planck and the expansion rate we measure locally. Another class of explanations involves unknown particles, perhaps new types of neutrinos or other lightweight particles that existed in the early universe and affected how it evolved. These hypothetical particles might have carried energy in ways that changed the dynamics of cosmic expansion, leaving subtle signatures in the cosmic microwave background that our current models do not properly account for. If such particles exist, they would represent entirely new physics beyond the standard model of particle physics, discoveries that would have profound implications for our understanding of matter and energy at the most fundamental level. Still, other explanations involve variations in the nature of dark matter itself, the mysterious substance that makes up most of the matter in the universe, but that we cannot directly observe. Perhaps dark matter interacts with other particles in ways we have not yet understood. Or perhaps its properties varied over cosmic time, changing how gravity shaped the evolution of the universe across billions of years. Each of these possibilities represents a significant modification to our current understanding, and none has yet been definitively confirmed or ruled out by observations. And then, in 2024, came observations from the James Webb Space Telescope that added new weight to this puzzle, not by resolving the tension, but by deepening it further. Webb, with its infrared capabilities and its position far from Earth's atmosphere, was able to observe the same Cepheid variable stars that Hubble had studied, and it did so with even greater clarity and precision. Some astronomers had hoped that Webb might reveal problems with Hubble's observations, perhaps finding that crowding from nearby stars had contaminated the measurements, or that other systematic effects had biased the results. But instead, Webb confirmed that Hubble's observations of Cepheids were essentially correct, that the distances measured by the SH0E's team were accurate, and that the high value of the Hubble constant they had calculated was not the result of observational error. This confirmation was both reassuring and unsettling, because it meant that the discrepancy could not be easily explained away by pointing to flaws in the local measurements. The Hubble tension appears to be real, a genuine disagreement between two different ways of measuring the same fundamental property of the universe, and this disagreement is telling us something important, something we do not yet fully understand. Perhaps our model of the universe is incomplete, missing some crucial ingredient that would reconcile these different measurements if only we knew what it was. Perhaps there are aspects of cosmic evolution, of dark energy, of dark matter, or of some entirely new phenomenon that we have not yet discovered or properly described. What is particularly humbling about the Hubble tension is that it reminds us of how much remains unknown, even after decades of remarkable progress in cosmology. We have learnt so much about the universe, about its age and composition and structure, about the galaxies that fill it and the forces that shape it. And yet, here is a simple number, a single measurement of how fast everything is expanding, and we cannot quite agree on what it is. This is the nature of science. Of course, this ongoing process of measurement and refinement and sometimes puzzlement. And there is something reassuring about the fact that nature still has surprises to offer, that the cosmos has not yet yielded all its secrets to our probing instruments and theoretical models. The Hubble Space Telescope has played a central role in revealing this tension, providing the precise measurements that made the discrepancy apparent in the first place. And it continues to contribute observations that help astronomers investigate possible explanations. Perhaps someday, through continued observations with Hubble and Webb and future instruments not yet built, we will discover what lies behind this mysterious disagreement. What hidden aspect of the universe we have been missing all along. But for now, the Hubble tension remains. A quiet reminder that something fundamental may still be waiting to be found, tucked away in the fabric of space and time, patient and unhurried, like the universe itself. For more than 34 years now, the Hubble Space Telescope has been circling our planet, passing overhead roughly once every 97 minutes. And in all that time, it has never truly rested, never closed its eye for long, but has instead continued to gather light from the universe with a patience that mirrors the patience of the cosmos itself. As of the most recent counts, Hubble has completed more than 1.5 million separate observations, each one a careful study of some corner of the sky, each one a question asked of the darkness and answered in photons. And this number continues to grow even now, even as you listen to these words and feel the gentle weight of sleep beginning to settle upon you. 1.5 million observations is a figure so large that it becomes almost abstract, like trying to imagine the number of grains of sand on a quiet beach at twilight. And yet, each of those observations represents a real moment when the telescope turned its gaze towards some particular patch of sky, opened its instruments to whatever light might be waiting there, and recorded what it found for astronomers here on Earth to study and understand. The final human hands to touch Hubble while it floated in orbit belonged to the astronauts of Space Shuttle Atlantis. During the mission designated STS-1255, which took place in May of 2009. This was the fifth and last servicing mission to the telescope, and the 7 crew members spent nearly 13 days in space, during which they performed 5 spacewalks to repair and upgrade the aging observatory. They installed 2 new scientific instruments, including the Wide Field Camera 3, which would go on to capture some of the most remarkable images in the telescope's long career. They replaced gyroscopes and batteries, components that had been working continuously for years in the harsh environment of low Earth orbit. And they repaired other instruments that had stopped functioning, giving them new life through careful work performed while floating weightless against the backdrop of our blue and white planet below. When the astronauts released Hubble back into its orbit for the final time, they knew they were saying goodbye not just for themselves, but for all of humanity, since no further servicing missions were planned, and indeed the Space Shuttle program itself would end just 2 years later. That gentle release, that careful letting go, marked the beginning of Hubble's final chapter, though it is a chapter that has proven to be far longer and more productive than many had dared to hope. In March of 2022, astronomers announced that Hubble had observed the most distant individual star ever detected, a discovery that pushed the boundaries of what anyone had thought possible for the telescope, or indeed for any instrument yet built by human hands. The star was given the name Earendel, a word borrowed from Old English meaning morning star or rising light, and it lies at an almost incomprehensible distance of 12.9 billion light-years from Earth. To speak of such distances is to enter a realm where ordinary language begins to soften and blur, where the numbers become so vast that they cease to feel like numbers at all and become instead a kind of poetry, a way of gesturing towards something beyond easy comprehension. When we say that Earendel is 12.9 billion light-years away, we are saying that the light which Hubble captured from this star began its journey toward us when the universe itself was only about 900 million years old, a mere infant compared to its current age of roughly 13.8 billion years. That light has been traveling through the expanding fabric of space-time for almost the entire history of the cosmos, crossing voids so empty that a photon might travel for millions of years without encountering a single atom of matter. And finally, after all that patient journeying, some small portion of that ancient light happened to arrive at just the right moment to fall upon the mirror of a telescope built by a species that did not even exist when the light began its voyage. Hubble was able to see Earendel only because of a phenomenon called gravitational lensing, which occurs when the gravity of a massive object, such as a cluster of galaxies, bends and magnifies light from sources behind it. In this case, a large galaxy cluster happened to lie along our line of sight to Earendel, and the tremendous mass of this cluster warped the fabric of space-time in just the right way to create a kind of cosmic magnifying glass, amplifying the light from the distant star by a factor of thousands and bringing it within reach of Hubble's instruments. Without this fortunate alignment, Earendel would have remained invisible, its light too faint to detect across such an enormous gulf of space and time. But the universe arranged itself in precisely the right configuration to allow us this glimpse of a star that burned brightly when the cosmos was still young and newly made. When the James Webb Space Telescope was launched in December of 2021 and began its scientific operations in the following year, some wondered whether Hubble's time had finally come to an end, whether this newer and more powerful observatory would make the older telescope obsolete. But that is not how science works, and that is not how light works either. And the two telescopes have instead become partners in a quiet collaboration that makes both of them more valuable than either could be alone. The James Webb Space Telescope is optimized for observing infrared light, the kind of light that is invisible to human eyes, but that carries precious information about the coolest and most distant objects in the universe, about the dust-shrouded nurseries where new stars are being born, about the atmospheres of planets orbiting other suns. Hubble, in contrast, excels at observing visible light and ultraviolet light, the kind of light that Webb cannot see as well, or in some cases cannot see at all. And this means that Hubble can reveal aspects of cosmic objects that remain hidden from its younger companion. When astronomers study a distant galaxy or a nearby nebula, they often want to see it in as many different kinds of light as possible, since each wavelength tells a different part of the story, and Hubble continues to provide observations that complement and complete the picture painted by Webb. The two telescopes work together across the electromagnetic spectrum, each contributing what it does best, and together they offer us a richer and more complete understanding of the universe than either could provide alone. Engineers and mission planners currently estimate that Hubble may continue operating through the late 2030s, assuming that its remaining components continue to function and that its orbit does not decay to the point where atmospheric drag begins to pull it back toward Earth. This is not a guarantee, of course, since spacecraft are fragile things and the space environment is harsh and unforgiving, filled with radiation and temperature extremes and the ever-present risk of collision with orbital debris. But the telescope has proven remarkably resilient over its long career, surviving failures and setbacks that might have ended lesser missions. The gyroscopes that help Hubble point precisely at its targets have been a recurring concern, since several have failed over the years and the telescope now operates with fewer than it was designed to use. But engineers have developed clever ways to work around these limitations, and the observatory continues to function with a grace that speaks to both the quality of its original construction and the ingenuity of the teams that continue to operate it from the ground. The scientific legacy of Hubble can be measured in many ways, but one of the most striking is simply the number of peer-reviewed papers that have been published using data from the telescope. That number now exceeds 19,000. a count that grows larger with each passing month as astronomers around the world continue to analyze Hubble observations, both new and old. These papers cover every area of astronomy imaginable, from studies of objects within our own solar system to investigations of the most distant reaches of the observable universe, from careful measurements of individual stars to sweeping surveys of galaxy evolution across cosmic time. The data that Hubble has collected over more than 3 decades represents a treasure trove that will continue yielding discoveries for many years to come, since much of it has never been fully analyzed and new techniques for extracting information from observations are constantly being developed. In a very real sense, Hubble's contribution to human knowledge extends beyond any single image or any single discovery, important as those have been, and resides instead in the vast archive of carefully gathered light that scientists will be studying for generations yet to come. There is something almost sacred about the journey that light takes to reach us from the distant universe, something that invites contemplation and wonder, even as it remains entirely explicable through the ordinary laws of physics. A photon that left a distant star billions of years ago carries no intention, feels no urgency, knows nothing of the vast journey it is undertaking. And yet, that photon travels onward through the darkness at precisely 299,792 kilometers per second, never slowing, never tiring, crossing distances so immense that our minds can only gesture toward them with numbers that have lost all intuitive meaning. Some of those photons, emitted by stars and galaxies in the early universe, have been traveling since before our sun existed, since before the atoms that make up your body had been forged in the hearts of earlier stars. And yet they continue their journey through the void, waiting for something to intercept them, waiting for some surface to finally receive them after all those billions of years of patient travel. And then, at last, some of those photons arrive at a small blue planet orbiting an ordinary star in an unremarkable corner of a spiral galaxy, and they encounter something remarkable, something that the universe had never produced before in all those billions of years, which is a carefully polished mirror suspended in a metal cylinder, built by a species that learned to wonder about the lights in the sky and then found ways to study them more closely. When one of those ancient photons strikes Hubble's primary mirror, its journey comes to a quiet end. But in that ending, there is also a kind of fulfillment, a completion of a circuit that spans not just space, but time, connecting the present moment to an almost unimaginably distant past. The information carried by that photon, the faint whisper of a star that may have died billions of years ago, is recorded and transmitted back to Earth, where human beings study it and learn something new about the universe and their place within it. This is what Hubble has been doing for more than 34 years now, catching photons that have been traveling since before the Earth existed and converting them into knowledge, into understanding, into a slowly growing map of the cosmos that we call home. And what that map has shown us, more than anything else, is the extraordinary vastness and age and beauty of the universe, and also, in a strange and humbling way, our own connection to all of it. The atoms in your body were forged in stars that lived and died long before our sun was born, and the light that Hubble captures from distant galaxies is the same fundamental phenomenon as the light that warms your face on a summer afternoon. We are made of the same stuff as the stars we study. And the light that connects us to them is the same light that has always filled the universe since shortly after its beginning. Hubble has taught us this, not through any single observation, but through the cumulative weight of 1.5 million glimpses of the cosmos, each one adding another small piece to our understanding of where we are and how we came to be here. As you drift now towards sleep, perhaps you might imagine yourself floating among the galaxies, weightless and unburdened, surrounded on all sides by the soft glow of distant stars. Each of those stars is a sun, and around some of them there may be planets where other beings also look up at their night sky and wonder about the lights they see there. The universe is very large and very old, and we have only begun to explore it. But thanks to Hubble, we know far more about our cosmic address than any previous generation of humans could have imagined. We know that we live on a small planet orbiting an ordinary star in a galaxy containing hundreds of billions of other stars, and that our galaxy is just one among hundreds of billions of galaxies scattered across the observable universe, each one an island of light in an ocean of darkness that stretches away in all directions farther than we can see or even comprehend. This is our home, this infinite expanse of space and time and matter and energy. And one small telescope circling the Earth has done more than perhaps any other instrument in history to help us understand it.